So today we're going to review solving systems of equations by graphing, substitution, and elimination. There is only one new item in here that you may not have seen before, but for the most part, all of this should be a review for what we're going to use for the rest of this unit, which is all over systems of equations. So the first few slides are all just a whole bunch of vocabulary and some explanations. So solving systems using tables and graphs, you need to know what a systems of equations is. It's two or more, so it could be 2, 3, 4, whatever, equations using the same variable. So they all have to have an x and a y, or they all have to have an a and a b. Then a linear system is just a set of two or more equations with the same variables where the equations themselves are linear functions, meaning they're the graph of a line. And the solution of a system is a set of values for the variables that makes all the equations true. So when you get a solution to your system, it must, if you plug it back into each equation within that system, it must make both of them or all three of them or however many equations are in that system, it must make them all true. Solving systems algebraically, we have a whole bunch of vocabulary that you need to consider. So when we talk about equivalent systems, they are just systems that have the same solutions. So you could have 2, 3, 4 systems, and if they all have the solution ordered pair of 1, 2, they're considered equivalent systems. They may have different looking equations within them, but if they all have the same solution, then they're considered equivalent. So in real-life situations, systems of equations will oftentimes have solutions that are not exact integers, decimals, fractions, positive, negative. So consider the rental car industry, for example. So the question is, which is the better value when renting a vehicle? So if we rent a vehicle from Rent-A-Hunk-O-Junk, they charge $29.95 per day and 43 cents per mile. Whereas Tom's Total Rex, they charge $45 per day plus 32 cents per mile. If you knew when the costs for both of these were the same, you could easily determine which one would be a better value for your personal needs. So it would depend really primarily on how many days you were planning on renting your vehicle. But at some particular point, at some number of days, the value of both of these are going to be the same. So that's an example of where we could use a system to kind of make a decision in our own personal lives. So here we go, let's review. This part may be new where you have not seen these words before. So we've got systems that are called inconsistent, consistent, independent, and dependent. And here are the definitions of what they all mean. So an inconsistent system is a system with no solution. So let's highlight some things here. So no solution means it's inconsistent. What type of systems have no solution? That would be parallel lines, because parallel lines do not intersect. So if they don't intersect, they cannot have a common solution. Sorry, there's the end of the day bell. Hopefully it won't get too loud. Then we have a consistent system, which is a system with at least one solution. So that means that it's either intersecting lines or the same line. So intersecting lines only intersect in one place.
Teachers, pardon this interruption, but please check your email for an email from the guidance office. It will come from Ms. Teague. Check your email. It's an important message for you from the guidance office. Thank you.
Sorry about that. So if they're the same lines, then let's just assume our system has 2 lines in it. If they're the same lines, then they're going to intersect each other an infinite number of times, which means that it has at least one solution. It just happens to have an infinite number of solutions. Intersecting lines only intersect each other once, so there's only one solution. Both these types of lines, or both of these types of systems, are considered consistent because they have at least one solution. So we are looking for at least one solution for it to be consistent. Then we have to look at, so a system is either inconsistent or consistent, but it can't be both. It can't have no solution and at least one solution, so it's either one of these two, and so these are where those ones fall into place. And then a system is either independent or dependent, but again, it's not both. So an independent system has a unique solution, meaning one solution and one solution only. So the only type of system that has a unique solution, one solution only, would be intersecting lines. So intersecting lines have a unique solution, meaning one solution, and they're the only ones that have exactly one solution, and that makes them an independent system. Then the last one is a dependent system. This is a system that does not have a unique solution. So it would have to be, and it can't have no solution. It just doesn't have a unique solution, meaning it doesn't have one solution, it has more than one solution. So the only set of lines that have more than one solution would be the same lines. Parallel lines have no solution, so they don't fall under independent or dependent. They're neither independent or dependent. So to be independent or dependent, there has to be some sort of solution. So let's highlight what's important here. What have not used? Blue. So a system that does not have a unique solution is going to be dependent. And so there is only one of those that does not have just one solution. And so that is going to be, what color shall I use? I'll use green. So that is going to be coinciding lines or the same lines, because they do have a solution. And I'll put in here that we call those coinciding. Okay. Then all this is a table so that you can kind of put it all together. So based upon number of solutions, the name of the system, and then what type of lines you have. So you have lines that either intersect, and that means they have one solution, or you have parallel lines that don't intersect, or coinciding lines which intersect each other an infinite number of times. So you might want to put an example of what these look like. So intersecting lines might look like this, where this is the solution right there. Parallel lines might look like this, and I'm not putting arrows on these, I'm just not taking the time. So there is no solution on that one. And then coinciding lines would be the same line intersecting itself an infinite number of times. So if you have one solution, according to what we just discussed definition-wise, it is going to be a consistent and an independent system. Parallel lines have no solutions, so the only thing they are is inconsistent, because you have to have at least one or more solutions to be consistent. Parallel lines are neither independent or dependent because they don't have a solution. Then coinciding lines have infinitely many solutions because they touch each other an infinite number of times along here. And so because they have a solution, they are considered consistent, but because they do not have one unique solution, they are considered dependent. So I want you to pause the video and I want you to determine, is this picture of you're looking at, what kind of graphs are they? Are they intersecting? Are they parallel lines? Are they coinciding lines? And then what is the name of the system? Consistent, inconsistent, dependent, independent. So pause the video and then I'm going to give you the answer. All right, so these lines are, let me get my black line up here. These lines are intersecting, and I'm going to write down here because you're never going to be able to see. So they are intersecting lines, and because they are intersecting lines, they are consistent because they have one solution, and they are independent because they have one unique solution. Oops, it would help if I spelled that correctly. Let's look at another one. All right, so this has the wrong title at the top, so you're going to need to change this to read coinciding lines. Because clearly we only have what looks like one line, but it's really two lines that are coinciding. So what I want you to do is stop the video again, determine what the name of this system is, and then restart the video, and I will give you your answer. Okay, so if they are coinciding lines, they have infinitely many solutions. Whoops. And because they have infinitely many solutions, they have at least one solution. They are considered consistent. But because they don't have one unique solution, they are considered, did I forget my N in consistent? There it is. Then they are considered dependent. So this one also has the wrong heading up here. It should read parallel lines. So if you have parallel lines, I want you to stop the video and I want you to try to determine, do you know the name of this system without looking at your notes? Once you figure it out, restart the video and I'll give you the answer. Okay, so if you have parallel lines, there is no solution. And because there is no solution, they are considered inconsistent. They are neither independent or dependent because they have no solution. So you can actually classify a system without graphing and determine whether it's independent, dependent, consistent, or inconsistent without ever graphing it. And we're not going to actually go through every one, but I'm going to describe to you how you can do it. So if each one of these systems, with the exception of one of these in here, all of these are in standard form. The lines are in standard form. If I knew whether the lines were parallel, coinciding, or just intersected, then I could tell whether they're consistent, inconsistent, dependent, or independent because I could tell what their solution is. So if you're to do it without graphing, you would have to take each one of these lines and put it into slope-intercept form so you could see the slope and the y-intercept. That would tell you whether you have two lines with the same slope, because if two lines have the same slope, they're either parallel or coinciding. Lines that have the same slope and same y-intercept are coinciding. Lines with the same slope but different y-intercepts must be parallel. Then if they have different slopes, then they must be intersecting. So I wouldn't have to graph any of these if I just looked at them in slope-intercept form. We're not going to take the time to do that, but you could. All right, so let's get down to business and actually solve by graphing. So I'm going to make this bigger so that you can see it and I can graph easier on it. Make it straight. That's good enough. Okay, so then in order to graph something, I have to have it in slope-intercept form. So I'm going to take this equation and I'm going to subtract x from both sides. And so I get y equals negative x plus 7. It has a slope of negative 1 over 1, or you can look at the slope as 1 over negative 1. Both give you a value of negative 1. And of course, remember that we reviewed graphing linear equations in the previous unit. So if it seems like I'm going fast, you're supposed to know how to do this. Then your b is 7. So I'm going to start off by graphing 7 on the y-axis, and then I'm going to stair-step my slope. So down 1 to the right one, and up 1 to the left. All right, so I'm going to connect this line. Okay, I'm doing a horrible job because I cannot use a straight edge. So sorry to say. Okay, so there's my blue line, and then so that's this one right here. Then I'm going to graph this line in red. So in order to graph this line, I'm going to have to subtract x from both sides. So I've got a negative y equals, if I subtract x, I get negative x plus 3. And then I have to divide everything by negative 1, which changes all the signs. That gives me a slope of positive 1 over 1 or negative 1 over negative 1. And I get a y-intercept of negative 3. So if I were to graph this, I would start at negative 3, and I'm going to stair-step my slope in the direction of the first line that I graphed. So if I go down 1 and to the left 1, down 1 to the left 1, I'm going away from that line. And really my goal is to get towards this line and find out where they intersect. And so I'm going to only use this slope up 1 to the right 1. So here I go. So up 1 to the right 1. So I just found their intersection, which is right there. So I'm going to stop there, and I'm going to actually connect because I don't really need to go any further because my whole goal is to find the intersection. So then you just need to name that ordered pair. So that ordered pair has an x value of 5 and a y value of 2. So that is the solution to this system. 5, 2 is found on both lines. They are the one ordered pair that both lines have in common. All right, so you do this one on your own and graph it and see what solution you come to. I am going to quietly do the solution so you can pause the video and then look at my work. I'm going to try not to talk through it. It's really hard for me, but I'll try. Well, this isn't very kind of them, now is it? I can't help but talk through this one. This is a stinker winker, so your slope is negative 1 over 3, and of course I paused to make sure that it solved things correctly, which I did, but here's what I'm annoyed about, and if I were you I would be too. This is the problem with graphing. You get a problem like this, where my y-intercept is a fraction. You can graph it, and I mean, it's graphable, but it's kind of a pain. So let me move this over. And I'm going to start on the y-axis at this ugly 1/3. I'm going to try my best to get it up there. So there we go. There's give or take 1/3, a little bit above 1. So I want to go in the direction of my first line. So if I go down 1, and to the right 3, I'm going to be going away from it, right? So I want to be doing this one, up 1 to the left 3. So up 1, so if I go up 1, I'm going to go to 1/3 above 1, and I'm going to go to the left 1, 2, 3. And that's actually where it's going to hit, which is not a nice happy integer point. And so that's why we bring this to your attention. So if I go up 1, 1, 2, 3, I land, I don't know, like right about here. And I'm going to draw my line because I've hit the other line, so why do I need to go any further? So then I'm going to estimate that ordered pair. Now, because I know I started at 1/3 above 0 here, when I go up 1, that's 1 1/3 for my y value. So as I go over here to the left, I know this y value is 1 1/3. So I'm pretty certain that this is 1 1/3 for my y, which I'm going to change it into an improper fraction here in a minute. But then I'm going to make a really good educated guess as to what my x value is. So I went over 1, 2, and then 3 would have put my other point here. So my x value is somewhere in between -2 and -3. So I'm going to guess it's like -2 1/3. I really don't know. I'm just kind of guessing. -2 1/3. And so we could change those to improper fractions if we wanted to, but this is just an estimate. You might estimate something slightly different. Now, the only way for me to know for sure is for me to take this ordered pair and then plug this x and y value into each of these and see, do I get 4 and do I get 1? So that brings us to some better methods for actually solving a system, because who wants to solve a system by graphing? It's just not accurate, at least in this situation. So let's look at solving by the substitution method. So I put down here for you your 3 steps. So you're going to solve one equation for one of the variables. So here's an example here. I will only use substitution. Again, it's not my favorite. I would only use substitution if one of my variable terms out of these 4, and it could be the y term too, it doesn't have to always be the x term, but I'm looking at the coefficients of my variable terms. If one of my coefficients or more, because then that would give me a choice, is a coefficient of 1 or -1, preferably 1, then I would choose to use substitution. And I would not choose to solve this equation for x because I'm going to get fractions. You want to find the equation and find the variable term that has 1 as its coefficient. So that tells me I'm going to solve the first equation for the x. If the second equation's y had a coefficient of 1, so it was +1, then I would have solved the second equation for y, or at least I would have had a choice between the two. So you'll solve one equation for one of the variables. So let's just start there. So step 1, I'm going to take x plus 3y equals 5, and I'm going to solve it for x. So that means I'm going to subtract 3y from both sides. So I get 5 minus 3y, and it's now solved for x. Then your second step says substitute this expression, that's this new expression here, into the other equation and solve for the variable. So because I used this equation, I have to take this and substitute it into the other equation's x, because that's what it says, x equals is this value. And we're trying to find where this x and this x are equal. So if I solve this equation for x and say it's got a value here of 5 minus 3y, then the other equation's x must also have a value of 5 minus 3y. So that's what we're going to do. Step 2, we're going to take the other equation negative 2x minus 4y equals negative 5, and instead of the x, I got big parentheses, minus 4y. So this is kind of like a composition, and we did that in the last unit as well. So all of this is going to go here, 5 minus 3y, and then do your math. So I'm going to distribute a negative 2, so I get negative 10 plus 6y minus 4y equals negative 5. Then collect your like terms, negative 10 plus 2y is equal to negative 5. Get your 2y by itself, so you're going to add 10 to both sides. So 2y is equal to, if I add 10 to both sides on the right side, negative 5 plus positive 10 is positive 5. And then divide by 2. Oh boy, oh joy, we get y equals 5/2. So again, I mean, if we had gotten that, so that's what the y value for both of our equations, that's what our y value, that's the y value that they're going to have in common. So if we were graphing, again, that might have been difficult to come up with. So then step 3 says back substitute into one of the original equations. So we're going to take this value for y, and you can substitute either here into that y or here into this y. I'm going to choose a y, or I'm going to choose a coefficient that if I plug this in, the 2 is going to cancel, if at all possible. So like if I put 5/2 in here for this y, 5/2 times 3 still gives me an ugly fraction. But if I put 5/2 and multiply it times negative 4, the 2 here is going to cancel with that 4. So I choose to plug it into the second equation. So here we go. Negative 2x minus 4, and instead of y, we were taking this value and we are putting it here. So 5 over 2, and I'm multiplying it, so I'm putting the 4 over 1 equals 5. So all we did was take this, oh, negative 5, my bad. Let me put that back in, negative 5. So all we did was take this equation here, negative 2x minus 4 times y, this is our new y, 5/2, equals negative 5. Then do the math. So I can cancel this 2 into this 4 2 times. So I end up with negative 2x. Then you have a negative 2 times 5, which is negative 10 over 1, so we don't write it over 1, equals negative 5. Add 10 to both sides. 2x is equal to positive 5. Divide by negative 2. X is equal to 5 over negative 2. And then finally, we should have added this fourth step. You cannot leave your answer like this. You have to write it as an ordered pair. If you don't, you're going to lose points. So then we have negative 5 over 2, comma, 5 over 2. So if you were to graph these two lines, that's where they would intersect. So we're going to move into my favorite method of solving systems is by the elimination method. So really, this method and the next one that we're going to look at are really the same method. This particular one is just the easier version of it. So typically both equations should be in what's called standard form. Essentially your variable terms are on one side and your constant is on the other. Ideally, that's how we would like our equations to be. Then you're going to add the system to eliminate the opposites of one variable. So in other words, you should have something that would look like this. 3x plus 2y plus equals 5. And maybe the other equation is x minus 2y equals 10. And if you look at this, you can see that the y's can be eliminated through addition. If I just add these two equations together, because the coefficients of the y's are the same number but opposite signs, these y's are going to cancel out. And you're going to end up adding the x's together. You get 4x is equal to 15, and you end up with one equation with one unknown where you can easily solve for that unknown. And so once you solve for that unknown, then you would substitute it back into one of the original equations. So let's go ahead and look to see how that works. So in this equation, I'm going to make it a little bit bigger so we can all see it. So in this equation, as you can see, the y's have the same coefficient but opposite signs. They have to have opposite signs in order to just add the equations together and get one of the equations to eliminate. So if I add these together, the y's are going to go away, they're eliminated, and I'm going to add down. So negative 2x positive 5x is a positive 3x equals negative 8 and 20 is positive 12. Divide by 3. And you get x equaling 4. So that's half of our solution. Then we're going to take that 4 and you have a choice. You can take the 4 and plug it into this x or plug it into this x. So you want to decide which equation looks easier to plug it into. I'm probably going to choose this equation just because there's fewer negatives in it. This one has 2 negatives. You know, it's all a matter of preference. So I'm going to take this 4 and I'm going to plug it in here. So here we go. 5 parentheses minus 8y equals 20. And so that 4 is going to go in place of that x. So I end up with 20 minus 8y equals 20. Subtract 20 from both sides. Don't freak out. Both of your 20s cancel. That doesn't mean there's no answer. If you had an answer for x, you're going to have an answer for y. The right side just equals 0. Focus on the variable. To solve for y, you're going to divide by negative 8. And so you get y equals 0 divided by anything is 0. So your final answer is 4 for your x and 0 for your y. So most students love elimination because the math is easy and it's pretty quick. Now, of course, if you get to a situation where your coefficients are not the same and not opposite signs, then you're going to have to multiply one or both equations by something in order to get that situation. So let's see how that works. So that brings us to a little bit more complication. So there's a whole bunch of stuff going on here. Basically, what you need to do is the following. So let me give you an example, and I'm just going to throw this out here. I don't even know if there's a solution, but what if I had 3x plus 2y equals 6 and negative 4x plus 5y is equal to 9. And let's say you're trying to solve this system. Right now, if I try to add the system exactly as it is, my x's aren't going to cancel, my y's will not cancel out. I don't have the same coefficient on both of these. So then you have to, what this whole thing is saying is you have to make a decision. Do you want to eliminate the x's or do you want to eliminate the y's? Sometimes to eliminate the x's or the y's, one is more work than the other. So you kind of have to determine, am I having to multiply both equations by something to eliminate them or just one equation? Am I going to have to multiply an equation by a negative to eliminate something because we don't like to multiply by negatives? So let's kind of evaluate our situation here. So for this one, if I wanted to make these two numbers into the same number but opposite signs, it would be 12. Whereas these, it would be 10. If you're having trouble looking at that, think of least common denominator. If these were the denominators in a fraction, what would you make them into? And essentially you're finding your least common multiple. So if I wanted to make these into 12, I'd have to multiply this whole equation by 4 to make that a 12x. And this whole equation by a positive 3. So positive 4, positive 3. To eliminate the y's, I would need to make them into 10. So one of these is going to have to be a negative. It doesn't matter which one. So I'd have to multiply this equation by either a positive 5 or a negative 5, and this whole equation by either a positive 5 or a negative 2. I'm sorry, a positive 2 or a negative 2. So both of them require having to multiply both equations by something, but I would probably prefer to get rid of the x's because I don't have to multiply by a negative. So let's look at an example that I didn't actually just throw out there. So look at this example here. So this is actually an example where you could actually use substitution to solve, because you have a variable term with a coefficient of 1 and a variable term with a coefficient of -1. So if you were left to your own devices and decided that you could choose whatever method you wanted to, you could use substitution here. You could solve this equation here for x and then plug it into this x. Or you could solve this equation here for y and plug it into this y. Now that tends to be a whole lot more work than elimination. So instead, ask yourself, what would I have to make the coefficients of the x's be to make them eliminate? This is 3 and this is 1. I would need to make them both 3. So this one already has the 3, so we wouldn't have to multiply this equation by anything. This needs to be a -3, so we would have to multiply this entire equation by -3. So far that sounds okay. If I were to eliminate the y's, I would have to make them both into a 2. If I wanted to make this into a 2, I'd have to make it, and it really needs to be a -2 so that it can eliminate with the +2. So I would only need to multiply this by a 2. So the whole equation here would get multiplied by 2. This would have to be multiplied by nothing. So I really only have a choice where I only have to multiply one equation by one number. But to eliminate the x's, I'd have to multiply by a negative. To eliminate the y's, I'd have to multiply by a positive. So I'm choosing to eliminate the y's. I always like to look for this plus-minus situation. So here we go. I'm going to multiply this entire equation by a +2. And when I say entire, I mean the entire equation, including that constant. So rewrite your rewrite your new equation, the whole system you need to rewrite, even the second equation, even though you didn't touch it. So 2 times 3x is 6x. 2 times -y is -2y equals 2 times 8 is 16. I'm going to rewrite the second equation. And now, when I add, the y's are eliminated. 6x plus x is 7x equals 16 plus 5 is 21. Divide by 7. And x is equal to 3. Then you need to take this value for x and you have a choice. I can substitute it back into this equation and solve for y, or I can substitute it back into the x into this equation and solve for y. This equation looks easier, so I choose to use equation number 2, and so that's what I'm going to do. So I'm going to take, and instead of the x, I'm putting in the 3 plus 2y equals 5. So again, I took this equation here, and instead of the x, I put in a 3. Now all we have to do is solve for y. So I'm going to subtract 3. I get 2y is equal to 2. Divide by 2. And I have y equals 1. And so then your final step is to write your solution. So these are intersecting lines that intersect at the ordered pair 3, 1. For this example, it's going to require a lot more work than the previous one. So you have to ask yourself, what are you going to do? So what would I have to multiply these by to make the x's eliminate? Or what would they have to be? I'd have to make them both into 15. I'd have to make both of these into 14. And I don't have a plus-minus situation going on at all, so it really doesn't matter whether I eliminate the x's or the y's. They're both equal amount of work. And I have to multiply one equation by a positive and one equation by a negative, so it really doesn't matter which. I'm probably going to choose to multiply this equation by a -3 and this equation by a +5. I'm hoping to eliminate most of my negatives. So when I rewrite it, I get, I'm going to get, let's see again, 15x plus 35y is equal to 75. And then if I multiply the negative 3 through, I get negative 15x minus 6y is equal to positive 12. Now when I add, the x's eliminate. 35y and negative 6y is 29y is equal to 87. When you divide by 29, goes into 87 3 times evenly. So now I have to find my x value. I have a y value, but I have to find my x value. So you need to decide, do you want to take this y value and plug it in here or plug it in here? I'm probably going to plug it into the top equation because it has no negatives whatsoever. You can plug it into this one. You and I are both going to get the same answer as long as we do our work correctly. So I'm going to take the 3x plus 7y, and instead of the y, I'm going to put this 3 in here. So I have 3x plus 21 is equal to 15. Subtract 21, and I get 3x is equal to negative 6 divided by 3, and x is equal to negative 2. So then write out your ordered pair answer, negative 2, positive 3. So then I want you to try this one on your own. So pause the video. I'll straighten this out. Pause the video, still crooked. There we go. Pause the video and then do your work and then restart the video. And I'm just going to quietly solve it on my own. So your final answer should have come out to be positive 1, negative 1. How'd you do? All right, so now let's look at systems that do not have a unique solution. So far we've only been looking at systems that have a unique solution. That means that they intersect once. So what does a parallel line system look like? And what does a coinciding line system look like algebraically? So we're still going to use elimination, and you have to decide, do you want to get rid of your x's? If I do, they both need to be a 2. Same thing with the y's, they would both need to be a 2. So I would have to multiply this top equation by a positive 2 no matter which one I chose to eliminate. So let's go ahead and do that. If I multiply the 2 all the way through to everything, I'm going to get a negative 2x a positive 2y, and a negative 4. Bring down the 2x minus 2y equals the 0. This time, when I add them together, both the x's and the y's eliminate. So don't panic if everything is gone. Remember that that means that there is a value of 0, and then equals negative 4. It is vitally important that you write down what you have left on the left and what you have left on the right, because you've got to compare the statement. Is it a true statement or is it a false statement? Since this is a false statement, there will be no solution. So not everything has a solution to a system. And so if it's a false statement and there's a no solution, that means that you're looking at lines that are parallel. All right, let's look at a different one. All right, for this one, if I want to eliminate the x's, I can make them both into 12. So I'd have to multiply this equation by 3. Actually, a negative 3, because I'd want to make it into a negative 12 to eliminate with that. If I want to eliminate the y's, I'd have to make them both into a 3, and so this one would need to be multiplied by a negative 3. So again, you see having to multiply one of the equations by a number that will eliminate both the x's and the y's. So you should kind of know right off the bat that they're both going to be eliminated. So when all of your variables drop out, you're either going to have a true statement or a false statement. So here we go. Negative 12x minus 3y is equal to negative 18. Bring down the positive 12x, the positive 3y, and the positive 18. Now add. Again, your variables are going to drop out, but you have to write, and your 18's canceled. And so the left side, if everything cancels, is 0. The right side, if everything cancels, is 0. So when you evaluate this, you realize that, well, that is indeed true. So if you have a true statement, you have infinitely many solutions. And if we have infinitely many solutions, we must have coinciding lines. And that's the end of today's video. Good luck. Let me know if you have any questions.